Assalamualaikum warahmatullahi wabarakatuh. We are from group 7 that we present for this week. There are 5 members in our group. There are Nurul Alia Farhana binti Zamzuri, Ainu Bazilah binti Muhammad Syari, Wan Nur Fatini binti Wan Nur Azmi, Nur Amira Alia binti Abdullah Sani, and Syah Atira Ilma binti Muhammad Sofi. Basically, we will tell you how to collect, analysis and report data from laboratory reactors. Firstly, let's see what to do in collecting data.
Bismillahirrahmanirrahim. My name is Ainur Bazilah binti Muhammad Syari, 1182334. Okay, now today we would like to explain about collecting, analyzing and reporting data. First, we will go to the collecting data. What is the purposes of collecting data? Okay, there are variety purposes why rate and kinetic data of different kinds are collected, which is the first one is activity, selectivity and catalyst life data are collected for catalyst selection. For the second one, chemical reaction, mechanism and kinetic data are collected for understanding the reaction at a fundamental level, modeling the reaction process and designing reactor. And for the third one, process variable data over a wide range of conditions are collected for designing large-scale reactors, for experimentally validating models, and for optimizing the catalytic process. Okay, next, we will go to the 3 major steps. The process of obtaining rate and kinetic data involves 3 major steps, which is, for the first step is selection of reaction and catalyst. For the second step is selection of reactor type. And the third step is analysis of data. Okay, this is the figure that shows 3 major steps, which I have said before. For the first step is select reaction and catalyst, and then we go to the select reactor and condition, and then we go to the data analysis, and then we can get the mechanism, rate expression, and process optimization. Note that statistical methods are used in step 2 and step 3 in the recycle process for the new experiment. Okay. For my part, I will explain about the select reaction and catalyst. Okay, first one, we go to the catalyst selection. Here is the catalyst properties and characterization. For the first one, catalyst or surface should be carefully prepared and pre-treated. So, it will be free of solid contaminants such as sulfur, chlorides, and carbon that might affect activity. For the second one, support effects should be avoided by studying reactions on single crystal of the active catalytic phase. Preparation method should be used which minimize decoration of the metal surface. Supported base metal catalysts need to be well reduced to avoid complication due to unreduced metal oxide. Okay, and then effect of surface structure and or dispersion should be considered in the case of structure sensitive reaction. Okay, then metal dispersion or surface area should be measured using proven and or standard ASTM method. Okay, ASTM is standing for American Society for Testing and Materials Methods. For example, method like hydrogen chemsorption or titration rather than, for example, we use hydrogen chemsorption or titration rather than CO chemsorption for metal. And then for the last one is methods of preparation and characterization and methods for calculating surface area and dispersion should be reported in detail carefully, because reporting these methods and the surface area or dispersion of catalyst samples should be a requirement for publication of specific activity data. Okay, next we will go to the reaction selection. There is the reaction condition for the reaction selection, which is the first condition is the clear absence of pore diffusional restriction, film mass transfer limitation, and heat transfer limitation. Okay, the data should be measured in the absence of pore diffusional restriction, film mass transfer limitation, and heat transfer limitation. And then for the second one, the second condition is the clear absence of deactivation effects. For example, of the activation effect is such as poisoning, choking, and sintering. And for the third condition is measurements over a wide range of temperature and reactant concentrated. The data should be collected the data should be collected over a wide range of temperature and reactant concentrated to facilitate valid comparison with data from other laboratories and provide a basis for determining the temperature and concentrated dependencies. And for the last condition is, data should be reported at specific condition of temperature, reactant concentration, and conversion. This specification should be used by reviewers and editors as minimum reporting requirement for publication in a journal. Okay, that's all from my part. Next we go to the next will be explained by my friend Alia. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Alia. Next, let's proceed to the second step of collecting data. So, the second step of collecting data is selection of reactor. There are two designs of reactor, which is differential and integral. Differential reactor are the reactor that induce a small conversion of reactor to product, and a fixed bed reactors with very low fixed bed height. While the integral reactor is a reactor that running in high conversion mode, while differential in the small conversion mode. Integral reactor is a fixed bed reactors with considerable height of the fixed bed. As you can see in the picture, you can see the difference between the reactor. The amount of catalyst in integral is quite high than the differential reactor. Okay, next, this is the characteristic of integral reactor and also the differential reactor. For the integral reactor, as I said earlier, integral reactor is run in high conversion mode. This is the formula of conversion, which is moles of A reacted over moles of A fed. For example, 100 gram per mole of A are fed and 70 gram per mole of A transformed to products. So from the information given, we substitute the value in the formula, so we get 70%. 70% conversion is achieved, which is mean a quite high value. The second is high temperature, and third is suitable for highly reversible reaction, and fourth is good for high specific product efficiencies. For the differential reactor, which is contra with the integral reactor, which is low conversion mode, low temperature, small concentration and temperature gradients, and lastly good for kinetic rate data. For the reactor, it is not suitable for kinetic rate data because it is has exhibit concentration gradient along the fixed bed. So if you want to run as an experiment which is low conversion mode, we use differential reactor. And if you want to run an experiment in high conversion mode, we use integral reactor. Okay, next, there is the example of reactor, which is batch reactor, CHTR and PFR. As we can see, there are differential form of batch reactor and differential form and integral form for PFR. If you want to know more information about this, I will share you the link in the comment sections. Okay, next is experimental design. What is experimental design? Experimental design is a subject to discuss catalyst testing, and it is important to collect meaningful and valid data. There are two important principles of experimental design. For the first is, experiment should cover experimental variables such as temperature, pressure, and concentration. For the second is, the number of experimental runs is needed to enable determination of accuracy, precision, and reproducibility.
Next, we are going to analyzing data. Before that, my name is Warno Fatini binti Warno Azmi, 11823336. Okay, for the objective of analyzing rate data from a reactor generally include, firstly, finding a rate equation or rate model. Second, determining catalyst activity, selectivity, and activity stability. Thirdly, determining effects of important process variables such as temperature, pressure, reactant, concentration, and space velocity on activity, selectivity, and stability. Okay, this is steps in analyzing rate data. Okay, for homogeneous reaction, we'll analyze it with the power law model. And this is the formula for analyze rate data. And the Lamre-Hinshelwood model for heterogeneous reaction. And this is the formula to analyze rate data for heterogeneous reaction. Since rate of catalytic reaction have a temperature dependence in accordance with the Arrhenius law, it is customary to plot the log of the rate constant, or the rate itself, versus 1 over temperature, and the slope is negative EA over R. If rate constants can be calculated without uncertainty from the rate data over the range of temperature, the plot of ln K versus 1 over T provide a true activation energy. That is a most reaction system, the calculated rate constant and it is apparent constant. It is likely to be a product of constants for several elementary steps. For Lamre-Hinshelwood rate expression for heterogeneous reaction, for heterogeneous catalytic reaction, the temperature dependence includes the temperature dependencies of equilibrium constants and the temperature dependence of the surface chemical process. It should be noted that Arrhenius plots involving apparent rate constants may not be linear over a wide range of temperature due to changes in heats of absorption with temperature and or shift in the rate determining steps. The difficulty to extract data. If reaction experiment conducted at sufficiently high conversion rate will surely include large resistance due to poor diffusion and film mass transfer. In this case, the observed activation energy will be much lower than the true activation energy of the chemically controlled process, since it includes the temperature dependence of the diffusion process. It is very difficult to extract useful kinetic data for the surface catalyzed reaction from rates collected under such conditions. This is a method to extract rate constants and concentration dependencies from rate data. The methods are integral analysis, differential analysis, statistical analysis, the method of initial rate, the method of half-life, and microkinetic analysis. Microkinetic analysis can be used to obtain and validate rate constants and activation energies for elementary steps. In our discussion, we are going to deeper on integral analysis, differential analysis, statistical analysis by my friends after this. So for my part, that's all from me. Thank you.
Thank you, Fatini. And now let's continue. I am Nur Amira Alia binti Abdul Sani, matrix number 1182339. Let's see what are the types of rate data. There are two procedures in analyzing kinetic data. Firstly, integral analysis, and secondly is differential analysis. These two procedures are generally used to obtain the laboratory reactors kinetic data. Now, let's take a look into integral analysis. In integral analysis, what we do is guess a particular form of rate equation. It is advisable to use simpler rate equation such as zero order, first order, second order, as they are irreversible. Then we integrate the equation that we guess and manipulate it mathematically. So if we integrate the rate expression, we will get the concentration profile. That means we will see the concentration versus time. Now we will plot a graph of concentration versus time. If we get a straight line, the rate equation that we guess is said to be satisfactorily fit the data. So we can assume that the rate expression is the correct one. Okay, now let's take, this is the example on how to integrate the rate equation if we assume that it is irreversible unimolecular type first order reactions. This is basically, actually we already have learned this with Dr. Zamir, and I hope you guys can still remember this. So in case of differential analysis, we feed the rate expression to the data directly without any integration, because the rate expression itself is in differential form. So we just put the rate expression into the data. So which one of these two is the beneficial method? Let's take a look into their advantages and disadvantages. For integral analysis, it is very easy to use because we need to guess a rate equation and then integrate it to fit the data that we obtained earlier. Secondly, it is very recommended when testing specific mechanism. Thirdly, it is relatively simple rate reaction, and lastly, integral analysis do not need derivative. The derivative that is mentioned here is that we obtain from the rate equation. For example, when the data are scattered, we cannot find the derivative that is needed. The derivative is also needed, but is in differential analysis. So, when does it happen? When the derivative cannot be calculated. For instance, when the reaction is really fast, the change of concentration is happen in short time, right? So, we may not get the exact kinetic as the change is insignificant. So, the data will generally scattered. Hence, it will not be a problem if you use integral method as derivative is not needed, unlike in differential method. In differential analysis, that it is very useful in more complicated data. The larger amount of the data and the data is not scattered, we said the data is very accurate. Hence, it is very practical in complicated situations. Secondly, differential analysis can be used to develop a rate equation to fit the data. Meanwhile, in integral method, we need to guess the rate equation as I mentioned before, but in differential analysis, we can develop the rate equation. Generally, integral analysis can be attempted in the first try, but eventually if you didn't get the successful result, you can use differential method.
Assalamualaikum warahmatullahi wabarakatuh. I am Syatira Ilma binti Muhammad Sofi 11823343, and I will continue presenting about reporting data from laboratory reactors. In this session, reporting of rate data will focus on the objective of good scientific reporting and the minimal requirements for reporting rate, kinetic, and activity data. So, the objective of good scientific reporting are, firstly, to communicate clearly, precisely, and consistently how the experiment were conducted. The second one, to know the important findings, and also to know the significance of this finding. Most literature papers fall short in areas of clarity and precision. The level of detail provided is usually inadequate for communicating either clearly or precisely how the work was done. Next, we should consider the minimal requirement for reporting rate, kinetic, and activity data, and the minimal requirement that we should fulfill are method of preparation and characterization should be reported in detail. Method for calculating surface area and dispersion should also be carefully reported. The procedure for collecting rate data should provide details regarding the catalyst and reactor. Next, experimental condition and the surface area or dispersion of catalyst samples must be reported in connection with specific activity data. And catalyst physical properties including particle size and geometry, BET surface area, pore size distribution, and active surface area need to be reported. BET here, or known as Brunner-Emmet-Steller, can be determined by physical adsorption of a gas on the surface of the solid and by calculating the amount of adsorbed gas corresponding to a monomolecular layer on the surface. Okay, continue again in the minimal requirements. The potential role of heat and mass transport limitation and catalyst deactivation should also be addressed. The OF data should be reported at specific conditions of temperature, reactant, concentration, and conversion. The OF or turning over frequency data should be collected over a wide range of temperature and reactant concentration to facilitate valid comparison with data from other laboratories and to provide meaningful data for determining temperature and concentration dependencies. Moreover, reporting statistical measures of reproducibility, variance, most probable error, and significance is also a necessity. Finally, it is crucial that the kinetic parameter be compared on an equivalent basis with those reported previously for the same catalyst and reaction in order to establish a measure of accuracy. All in all, powerful reporting reduces the time needed to merge, process, and analytical data, visualize, and identify key reaction events, and develop reports which lead to better decisions for improved process development and optimization. That's all from me and my group. Thank you.